Good morning, everyone. This is take 2 on this video. I recorded the whole darn thing yesterday and unfortunately had software issues, and I'm now repeating it. So hopefully today goes more smoothly. So really quick introduction into magnetic field theory, and then some extra little clips that I will post up in this second area in this video assignment for you. So kind of a few smaller but more bits to this one. Quick notes for you. We're in chapter 12 of your textbook, but of course we're going to be bebopping around a little bit as I pull in some of those interesting technologies from later on in our textbook. Okay, a quick little intro into this slide here, and I will be talking about this in more detail later on. But a little nod to our beloved home planet Earth, seen completely not to scale relative to the sun over here on the left, just because it has its own magnetic field, as I'm sure you all know. And that magnetic field is what keeps it safe and makes life on the planet even possible. And so pretty cool that good old little magnet, creating a magnetic field, can protect all life on Earth. Okay, I could get off topic on that one and talk for a long time. It is coming up a little later on, but we'll crack on with some essentials in terms of definitions and theories and all that kind of thing, and make sure our vocabulary is all on track. Okay, so to start us off, it's quite early in the morning, so apologies for the frog in the throat. That is going to keep ribbiting back at us, I'm sure. So as I was saying, quick definition: magnets are anything capable of producing a magnetic field, and magnetic field is just like but not, just like gravity and electricity, in that it's providing action at a distance. So we can't really see any physical connections, but it is still able to influence other things, such as what we call a ferromagnetic substance. Now, chemistry people, this probably looks familiar to you. Ferro stands for substance made of ferrum, which is the old name for iron. And in fact, ferromagnetic substances include iron, as well as some others. Here we've got nickel, cobalt, and then the group of alloys, which are, of course, a mixture of different metals. My favorite one is alnico. I don't know why it's my favorite. I just like the sound of it. It sounds like some sort of crazy car truck like the El Camino, but only for chemists, the alnico. Anyways. Okay, perhaps I should have had more caffeine before starting this. Oh dear. Okay, so in terms of magnets, we have two different sort of broad categories. We have permanent, and you'll be surprised to hear non-permanent as the other category. Permanent magnets create their own magnetic field all of the time. So they are naturally magnetic and will generate that action at a distance ability all of the time. Certain metals, for example, will be permanent magnets coming up soon. Temporary magnets are, for example, something like an electromagnet. I think I have electromagnet. Yeah. Something like an electromagnet, which is a magnet that you plug in, essentially. So electricity provides the ability for us to generate a magnetic field, but we can turn it on and off again. And for example, if you've ever been to a car crushing yard, they will have these huge magnets on like a crane-like structure. It looks like a hangman, but anyways, it's not, and it's an electromagnet. And then your innocent old car sitting here will be picked up by that magnet and taken off to the crusher, for example. So this is a very, very powerful electromagnet and uses a lot of electricity in order to generate a strong enough electric field, magnetic field, in order to pick that car up. We also have some temporary magnets that are kind of induced magnetic fields, and that means we can take something like, say, a piece of cutlery, take a butter knife. It's easier to visualize with a butter knife, and then if you stroke that with a magnet, then that can infer some magnetic field onto that piece of cutlery. Sometimes this happens even in commercial dishwashers. Your serving staff will, or your kitchen staff will take out the cutlery and find that they're sticking together in the dishwasher. Not to a huge extent, but strongly enough that it's noticeable. And that is a temporary magnet generated by that dishwasher. So we will talk more about those temporary situations when we talk about something called domain theory in a little bit, possibly in a second tiny little video right at the end. Okay, so moving on with our vocabulary, just to remind ourselves, when we use the word pole, it means an opposite area, so opposite region. For example, here it says a region where the magnet has the greatest influence, and that every magnet is bipolar. So it just means it has two poles. So two, bi for two, polar for opposites, two opposites. And we call those north and south. Now, there is something called a monopole. We're not going to cover that, but you can have a look at that. And if anyone is interested, I can look up some info and send it along to you. But for us, everything will have a north pole and a south pole, and those are our two opposites. Between the north and south pole, we will generate a magnetic field, kind of in a similar way that we had that dipole situation with two electric source charges. And when we had that situation, we would generate an electric field from positive to negative, always that same direction, as defined by Terry, good old Terry, the test particle. In that same way, if you look down here, we're always going to have, this is coming up in our slide, but just since we're looking at this beautiful bar magnet here, we will always have lines, field lines running from north to south. Okay, so not described by Terry any longer. That is just a big important rule that we need to remember. This thing is a bar magnet. You probably played with these in elementary school when you're learning about magnetism for the first time. We're going to talk about the magnetic law in 2 seconds. But just to compare a bar magnet and to show you another shape, and that is the U magnet. I wonder why we call it that. But it is also quite commonly called the horseshoe magnet. It's essentially a bar magnet like we've got here on the left that has been bent around into a curve, or in fact a U. And this amazing diagram, just to show you that we would still have field lines running from north to south. So straight down between them, maybe curling around a little bit on the ends like that, but definitely still from north to south. The law of magnetism is similar to the law of charges that we've looked at before, and that simply says that like poles repel and opposite poles attract. It's pretty much the same as the law of charges, here just reflecting its context in magnetism. These poles will create field lines. Now, these are invisible field lines. When it says field lines, this is the whole action at a distance, that orb or sphere of influence around the magnet. But we visualize that like those lines that we saw in the previous slide, and in fact are here as well. One thing to note that with electric sources, when we're drawing electric field, we have to count the size of those source charges. So +1 will have so many lines, +2 will have so many lines. If you're looking at an isolated system like a magnet here, you're always going to have the same number, and I counted them earlier, so I can tell you that there's 10 coming out of north. You will always have the same number going back in to south. Okay? Yeah. Okay. Here is just a really pretty picture of some of those field lines as defined by some little iron filings. Now, those little iron filings are in fact little rods or cylinders themselves, and they will line themselves along those magnetic field lines, allowing us to see the magnetic field. So it's a way of us observing those field lines that are going to be generated between them. Okay? And again, reminder, always from north to south. I know that green is not very dramatic, is it? All right. Interestingly, we can have, this is a two-dimensional representation, it's just iron filings on a piece of paper. If you look closely enough at the poles where the concentration of the field is the greatest, then you will notice some three-dimensionality, even on a piece of paper. Here's a slightly better rendition of that three-dimensionality. You can maybe see, I'm going to switch to a dark blue here. You can maybe see some more dimensionality. If I was connecting, it's always going to be from north to south, but you can see curves happening on the edges that would loop back around in here as well underneath. But also, I don't know if it's super easy to see on the North Pole, but on the South Pole here, you can see it's like out of the page, into the page kind of angle, so your Z dimension as well. Maybe easier to see back here when we're going into the page in the negative Z, and then we would be coming back in the positive Z into that South Pole. All right. We will get to play with some of this stuff in class, guys, so that's kind of exciting. This is one of those super duper, always a test question type situations, subtle hint, subtle hint. It says important magnetic poles do not attract nor repel charges. Magnetic fields will influence an electric charge, but it is not an attraction or repulsion to the poles themselves. Okay, so we get a deflecting force. Excuse me, that force, which will be a magnetic force. I'll just read through that quickly with you, maybe, rather than having you try and read that and listen to me going off piste there. So whilst a magnetic field can exert a force on a charge, the poles of a magnet do not attract, nor repel a charged particle. The force exerted is a magnetic force, coming soon to a classroom near you, and that's the symbol up here. Of course, it's going to be in newtons, it's a force, so exactly the same way. Wait till you see the units for magnetic field, though. They're kind of crazy. Love it. All right, really quickly, as promised, Earth's magnetic field. Now, cast your mind back into the time before when we were exploring the planet by ships for the first time, and scientists and sea captains and navigators and all that kind of thing would use a compass in order to do it. Now, because of that, we have some definitions of north and south on our planet that don't necessarily match the magnetic field definitions. I'm just going to show you that. And just a reminder that what a compass actually is a small magnet itself floating on a pivot point which allows it to spin. So, where's my compass? Here's my compass over here. I think I have another one, don't I? Oh yeah, there it is. I just wrote over top of it. Of course I did. All right. So just really quickly read through this. It says the north pole of the compass magnet will point towards the south magnetic pole, which is the north geographic pole. Really super duper confusing. Just think of it this way. The compass points north. So that is the north pole on our magnet, which is the little red bit here. The north pole is going to point to the south magnetic pole. So remember, opposites attract in terms of magnetic law. So north here will attract south of our Earth's magnetic field. Now the north and south are attracted, but you can see our south pole of our magnet is slightly tilted. Please note, we do not have a giant bar magnet embedded into the planet Earth. We'll talk about what that is in a second. This is just for illustration purposes to help us visualize. It is slightly askew, slightly off tilt, which is why we say we have a different north geographic pole and a north magnetic pole. That's because our magnetic field is askew, okay? But just remember, north geographic pole attracted to the south magnetic pole. And even though that is the case, we still have to remember where polar bears and Santa Claus live, and that is in the geographic north, which is the magnetic south. That is not magnesium, that is magnetic. I'm just being lazy. There we go, magnetic south. Okay, and down here are penguins, despite some misleading soda pop commercials at Christmas time. Penguins only live in the geographic south. and various parts. Well, anyways, I just got off topic on penguins. Anyways, which is the magnetic north. That's an A. Here we go. Polar bears, geographic north, magnetic south. So what's going on with this Earth, and why does it have this magnetic field? Well, super quickly, and I am going to show you some other stuff coming up soon in a second little clip. But for us right now, Earth has a solid inner iron core, okay? But that's not the only inner core, which is kind of weird. Core means at the center. So at the center, we have a solid iron bit. In the center, around the center, do you like that? So the outer core is a bunch of molten fluids, which is a high energy mixture under incredible pressures and temperatures of ions, so charged particles, metal ions, and all sorts of fun stuff like that, that spin. And that spinning is because of our planet spin, the planet spin, which is the result or the leftover, the hangover from its formation impacts. So because our Earth spins on its axis like this, we get the molten fluid spinning. It's spinning around that iron core, and that interaction, that friction that exists between the outer edge of the iron core and the molten fluids under high temperatures, high pressures, generates electrical currents. Anytime you have a moving charged particle, as we will see coming up soon, so a little more theory and another superhero in the physics world to talk about there, anytime you have a moving charged particle, you can generate a magnetic field. Now here is a visualization. This is from the NASA website. The citation is in the notes for this PowerPoint, which is posted. This is showing you, here's our lovely little planet. This is showing you our field lines now, from north to south, of course. Here we go, from north to south. South geographic pole, north magnetic pole, from north to south like this. And we're getting our magnetic field sort of scrunched in there on both sides. You can see, however, we have a slight discrepancy in terms of shape with our magnetic field. This side is more cylindrical, slightly compressed as we look this way, whereas this one is kind of stretched out as we look this way. And that's because the sun is on this side and it's exerting lots of solar wind. And those solar winds, full of kinetic energy, full of charged particles, full of radiation, all that kind of thing, they're impacting those field lines and actually squashing it. So you can see this red line here, artist's rendition of sort of like a shock wave coming in and squashing our magnetic field. Here's from the NASA government website, the magnetosphere of the Earth. The orange coming in, again, this is the sun. These are the solar winds coming in this way, compressing this side of our magnetic field and causing it to stretch out on the far side. Now we've got some other stuff here that's coming up on a second little clip. Oops, But I will give you sort of the Coles notes right now that we're going to talk about. So we've got our field lines wrapped around our planet like this. And what happens is that the solar wind carrying all these little charged particles, the radioactive particles, are going to bombard it. And once they come close enough to be affected by the magnetic field, they're going to experience a force. And that force is going to cause these particles to spiral around that magnetic field. Now, this is going to take those charged particles closer and closer and closer to the Earth. And once they get within our atmosphere levels, then they're going to interact with gases. So the the gases in the atmosphere, primarily nitrogen and oxygen, that we're going to see this. When they bombard these atoms, they're going to excite the electrons. The electrons are going to have all this extra energy. Then they give back that energy as light. Now, once they give it off as light, we can actually see it as visible light, and this is our aurora borealis, or the northern lights that we see. More little clips coming up soon with some pretty pictures for you. I think I've got one coming up. Just a reminder that we also have southern lights, so we also have them on the South Pole as well, aurora australis and the aurora antarctica. So here's the textbook description. It says, when a charged particle enters a large magnetic field at an angle between 0 and 90 degrees, the particles will spiral along the field lines towards those poles. There they go. Collisions between charged particles from the sun and the atmospheric gases create the visible lights. And there we go. There's a pretty picture, but there's more coming up soon. What I'm going to do is stop this video clip now. I'm going to, in a separate section in your video assignment, pop up some other links, just so we can conform with copyright laws, etc., in a posted video. Okay? So coming up soon, more on cool stuff like the magnetic field of the Earth, aurora borealis, and something cool that you may never have heard before. Dun dun dun! On that cliffhanger. Toodle pip.